You are familiar now with some curious drag phenomena. You have seen that at low air speeds, a smooth ball has less drag, while at higher air speeds, a roughened ball has less drag. You have seen that streamlining reduces drag in air, while it increases drag in glycerin. You have seen that in a certain range of speed, the drag of a sphere actually decreases while the speed increases. At this stage, matters look pretty complicated, but actually, there is order and logic in all you have seen. There is only one way to discover this order and logic, and that is by thinking in terms of the fundamental concepts and principles of fluid mechanics. The first concept is that of a continuous fluid. We know that matter is really made up of billions and trillions of molecules separated by empty space. But on a scale of size which is very large compared with molecular distance, matter appears to be continuous and unstructured. Rather than think of all the individual molecules of the real fluid, therefore, it is convenient to replace the real fluid by what we call a physical model. This model has neither molecules nor structure. It is continuous, and it has certain average properties which represent the statistical behavior of the countless molecules of the real fluid. One such property is the density. Let us think of a very small lump of fluid, smaller even than this droplet, which nevertheless contains many molecules. The average density is defined as the total mass of all the molecules of the lump to the total volume of all the molecules with their surrounding space. Density is mass divided by volume. But each lump or particle of fluid may have different properties. For example, not all particles have the same motion, as you can see by looking at the flow in a sink. To make it easier to understand such complex motions, we imagine the entire body of fluid to be subdivided into many small fluid particles, each having its own trajectory and history. Each and every such fluid particle obeys Newton's law of motion. Consequently, we can learn a great deal about the flow as a whole by focusing our attention to begin with on the dynamics of some typical fluid particle. Suppose that a tiny cube of water in the jet were dyed a bright color, so we could follow it easily. Let us isolate this cube mentally from the surrounding water, and then let us consider the forces acting on it, and how these forces influence its motion as it flows from the faucet, swirls in the sink, and departs down the drain. Let this block represent, on an enormously magnified scale, our fluid particle. While many different kinds of forces may act on this particle, they may all be put into two categories: body forces and surface forces. Body forces act at a distance: gravitational, electrical, and so on. They act on the bulk of the material, hence the word body. If this cube were a particle of water in a quiet reservoir, it would be pulled downwards by the force of gravity. But the particle is motionless, so some other force must be present to counterbalance the weight. This other force is called the surface force. While body forces act at a distance, surface forces act by direct contact between the particle and the surrounding medium. And as the name implies, surface forces are exerted directly on the 6 surfaces or faces of the cube by the surrounding fluid with which it is in actual contact. On each face of the cube, equal and opposite forces are mutually exerted, between the fluid inside the cube and the fluid outside. The surface forces act on the fluid directly, while the body forces act at a distance. Surface forces act by direct contact between the particle and the surrounding medium. And as the name implies, surface forces are exerted directly on the 6 surfaces or faces of the cube by the surrounding fluid with which it is in actual contact. On each face of the cube, equal and opposite forces are mutually exerted between the fluid inside the cube Let us look at one of the faces of our particle. The greater the surface area, the greater the surface force. And so it is convenient to think in terms of the force per unit area. This ratio of force to area is called the stress. For instance, if we push with 5,000 dynes on this face having an area of 50 square centimeters, the average stress, or pressure, is 100 dynes per square centimeter. The distributed nature of the stress is indicated by these arrows all over the surface. Suppose now that we push on the opposite face with 5,000 dynes. Then there is no net force to accelerate the particle. And so the amount of pressure acting on any one face is in itself unimportant to the dynamics of the particle. But now, suppose that we push on the second face with a force of 7,000 dynes. Then there is a net pressure force to accelerate the particle. So it is differences in pressure that count. The greater the pressure difference over a given distance, the greater is the net pressure force per unit volume of fluid. This rate of pressure change with distance is called the pressure gradient. Thinking again of our cube as a particle in a stagnant tank, we see that the weight can be supported if the pressure on the lower face is larger than the pressure on the upper face. The right-hand side of this U-tube is open to the atmosphere. Let us create a higher pressure on the left-hand side. Now we have equilibrium, and we see that the weight of the unbalanced column of liquid is supported by the difference between the high pressure at the bottom and atmospheric pressure at the top. Now suppose that the pressure difference is applied in a horizontal direction. Low pressure here, high pressure here. Gravity acts downward, and so does not contribute to the horizontal balance of force. The net pressure force is not balanced by any other force. According to Newton's equation of motion, therefore, it produces a horizontal acceleration. This arrow represents the acceleration. In this horizontal tube, we have a colored slug of liquid with atmospheric pressure at the open end and, for the moment, atmospheric pressure at the other end. Now watch. Force equals mass times acceleration. So far, we have considered only stresses normal to the surfaces of the fluid particle. Moreover, we have thought of the fluid particle as being rigid, like this block, so that it could be displaced and turned, but not deformed. Actually, fluid particles can and do undergo great changes in shape, even more easily than this block of foam rubber. Like the foam rubber, fluid particles resist deformation. But while the resistance of a solid depends on the amount of deformation, the resistance of a fluid depends on the rate of deformation. The fluid property, which represents the magnitude of this resistance, is called viscosity. Some fluids, like water, have a comparatively small viscosity, while other fluids, like corn syrup, have a comparatively large viscosity. To be more precise about viscosity, suppose that an initially square piece of fluid undergoes a certain amount of shear deformation, as measured by this angle. Then the viscous resistance appears in the form of tangential or shear stresses required to produce this shear deformation at a certain rate. In fact, we define the viscosity as the ratio of the shear stress to the rate of shear deformation. Viscosity is shear stress divided by rate of shear deformation.